All right, hello and welcome back, everybody. We're moving on to the section worked examples for diagonalization and non-diagonalizability. And I didn't quite cover what it meant for a matrix to not be diagonalizable in the last video, so let's just cover that really quick. Biggest statement: not all matrices are diagonalizable. So don't imagine that they are. And as a subset of this, you can tell if they aren't by testing the span. So we're back in span world. The span of the set of eigenvalues or eigenvectors. Span of the set of eigenvectors. If the span of this set is not equal to V, whatever vector space you're looking at. So if that span is not equal to V, then the matrix is not diagonalizable. This is often the case. Actually, it's necessarily a subset of the case if M, the matrix, does not have n, and as before, this is its size, its length, distinct eigenvalues. It may not be diagonalizable. It in fact may also be diagonalizable. This is kind of a tricky thing. You still have to test the span condition, but that's the way that you can tell. Let's just look at an example of one matrix which isn't. So example of a non-diagonalizable matrix would be just the two-dimensional matrix 1, 1, 2, 0 is not diagonalizable. And we can just see this by testing. Let's go ahead and compute, let's compute the eigenvalues. 1 minus lambda 2, 0, 1 minus lambda. The determinant is 1 minus lambda squared minus 2 times 0. So the characteristic equation is when that's equal to 0. So 1 minus lambda squared is 0, or rather lambda equals 1 of multiplicity 2. And then if we go ahead and try to find some eigenvectors, let's just do that really quick. So when lambda equals 1, we get 0, 2, 0, 0 against x1, x2. This needs to be 0, 0. The first line tells me that 2x2 is 0, so x2 has to be 0. The bottom line tells me 0 equals 0, so this is an informationless equation, which means that my relationship, quote unquote, for eigenvalues is, well, I know that x2 has to be 0, x1 can be anything. You can be anything if you believe in yourself, x1. And so our eigenvector corresponding to lambda being 1 is just x1. x2 is forced to be 0. And then in like our final step, we could send ourselves to just letting x1 be 1, 0, and that's the only eigenvector. Okay, so what's the span of this set, 1, 0? Well, it's definitely not equal to R2, which would be the vector space, the matrix acts on. Right, the span of 1, 0 is just a one-dimensional space. So that's one quick way of just verifying that this was a non-diagonalizable matrix. Because like you would try to go through your diagonalization process and construct capital X as a matrix of 2 eigenvectors, but you only have one. You know, there's no second eigenvector, so you're kind of stuck. It doesn't exist. But there's also the case where maybe 2 of them did exist, but they were linearly dependent to each other, in which case X inverse doesn't exist either, and so you still run into problems. So you need that span condition. That span condition is really what you're looking for. This is the domain and codomain of M. So that's really what you need to be diagonalizable. To that end, we'll just encounter 2 versions of diagonalizing a 2x2 matrix today. And in particular, we haven't really seen any complex eigenvalues yet, or even complex matrices. I've kind of been doing you a disservice in not giving you enough examples of some complex matrices and eigenvalues, so we'll go ahead and analyze some of those. So first example, let's diagonalize the matrix 0, 1, -1, 0. This is a rotation matrix, by the way. And we won't get too much into why this is a rotation matrix, but you can kind of think if you start out with your two canonical R2 vectors, 0, 1, and 1, 0, and both of them in R2, and then you act this matrix on them. Let's go ahead and act 0, 1, negative 1, 0 on the first one. So let's act it on 1, 0, and we'll end up with, it looks like the inner product up top is a 0, and the inner product on the bottom is negative 1. So that's my image. And then let's suppose we do that again on the other vector, 0, 1. The output is going to be 1 and then 0. And so what do we get out of this? The image is the vector 1, 0, which points to the right, and then 0, negative 1, which points down. So this is rotation by negative 90 degrees, or negative pi over 2. Because basically the blue's shifted down 90 and the red is shifted down 90. Or I guess those are the colors yellow and cyan when I've inverted everything. So that's why it's called a rotation matrix. And let's just use our intuition. Recall when I introduced the complex number I had said it corresponded to rotation by 90 degrees. So do we have any intuition on what the eigenvalues might be here? Well, anyway, let's go ahead and diagonalize. So procedure for diagonalization. Step 1, we need to find all eigenvectors, eigenvalue, eigenvector pairs. And in this case, we'll just start by computing our characteristic equation. So there was a 0, and then minus lambda. There was a 1, there was a negative 1, and then another 0 minus lambda. And so our determinant's going to be negative lambda squared minus 1 times negative 1. So we're going to get lambda squared plus 1 equals 0 as our characteristic equation. And what are the roots there? I could use the quadratic formula if I want, but I can also just subtract 1 to the right-hand side, take a square root. I have plus or minus the square root of negative 1. And what do you know? My eigenvalues are plus or minus I. Maybe I'll write them as I and negative I. So that makes a lot of sense. When you have a rotation matrix, your eigenvalues correspond exactly to that rotation. And let's go ahead and find the eigenvectors corresponding to each of those. So when lambda is I, our matrix becomes 0 minus lambda, right? So you get minus I, 1, 1, and minus I, acting on the vector x1, x2, and we want this to be equal to 0, 0. So that's going to send me to negative I x1 plus x2 is 0, and it's going to send me to x1 minus I x2 is 0. And I can solve either of these for the other, and I get x2 is I copies of x1. The second line would give me the same. Certainly this is because I'm always just looking for a relationship. So the relationship with my first eigenvector, x, which I'll call x sub I, the sub I because I chose I as my lambda, will be x1, x2, where in particular x2 is equal to I copies of x1. And if I want, I can actually send myself to my final step where I just allow x1 to be 1. And so in the second case, it's I times 1, or I. And this is associated to lambda equals I. Here's my first eigenvector pair. We can do the lambda equals negative I case. This is going to send me to 0 minus negative I, also known as positive I, 1, negative 1, and positive I, against x1, x2, gives me 0, 0. So that's going to send me to the system of equations. I times x1 plus x2 is 0, and negative x1 plus I x2 is 0. In this case, the bottom equation is a little easier to solve for. We see that x1 is I copies of x2, but we would get the same from the other equation as well. That tells me that x vector sub negative I, or the vector corresponding to minus I, is x1, x2, but I know x1 in terms of x2, it's I copies of x2, and x2 in the second component, which if I want, I can let x2 be equal to 1, then recover that x sub negative I is I and 1, associated to lambda equals negative I. So step 1 in diagonalization. Step 2, we always establish this capital X matrix, which will be the first eigenvector, I'll call it x sub I, and then the second eigenvector, x sub negative I. And those just come directly from above as 1, I, 1. And we can find x inverse as 1 divided by the determinant. So I'm looking at 1 times 1 minus I times I squared is negative 1, so I get plus 1 here. And then we're left with swapping A and D, which they swap to each other, and putting a minus sign on B and C. Or in other words, I could call this 1/2 1 minus I, and 1. In step 3, we want to construct our diagonal, which will just be our 2 copies of lambda, the positive version and the negative version, which in this case, the first lambda associated to our first eigenvector was I, and the second lambda was negative I. The rest of my matrix is zeros. And then in step 4, we have our actual diagonalization. M, our original matrix, which in this case was 0, 1, negative 1, 0, the rotation matrix, can now be written as x dx inverse. If I translate all of those down, I have 1, I, 1, times d, which was I, 0, 0, minus I, times x inverse, which was 1/2, 1, negative I, 1. Now, the fact that you're noticing this whole complex conjugate situation going on, even between these two, is no coincidence, but it's also not something that I'm going to really discuss too much today. If you take a course in complex analysis, you'll find out why this is. But let's do one final step here, even though I've technically finished my diagonalization. It is this final row. Let's do one last step, and let's verify the diagonalization. This will give us some practice with matrix multiplication. So let's just go ahead and compute this entire product out and hope we end up with M when all is said and done. So to compute the entire product out, we have to make a choice over which matrix multiplications we want to play with first. I'll choose the ones on the left. It really doesn't matter. You just got to make a choice. So let's do this first, and then let's finish off by doing the rest of them. So the first matrix multiplication, I'm doing all columns on the right and all rows on the left. Then I'm going to take inner products here, but this is something I didn't make too clear. When I said all inner products for matrix multiplication, we are not taking conjugates. So technically, if I were doing a true inner product of these two vectors, I would have to take a complex conjugate of the vector on the right. This does not occur when you're doing matrix multiplication. So I use the language inner products, but you really shouldn't think about it as inner products. Think about it as like the real version of inner products, where you're not going to do some complex conjugates. Anyway, we're going to do these inner products between the columns and the rows, and we will get I plus 0 in the top left. We will get 0 minus I squared in the top right. We will get I squared plus 0 in the bottom left, and we will end up getting 0 minus I in the bottom right. If I decide to simplify all of that, I can call it I over here, negative I over there. This will turn it into 1 and negative 1. So the 1 here, negative 1 there. Then we'll multiply by the 1/2, 1, negative I, and 1, and perform this product now. And the 1/2 can come along for the ride. We're not going to worry too much about that. So the 1/2 is sitting out front, and then we're considering everything on the right as a column and everything on the left as a row, and then taking the inner products. So now I have an I minus I in the top left. I have a negative I squared plus 1 in the top right. I have a negative 1 plus I squared in the bottom left, and I end up with a positive I minus I in the bottom right. When I simplify everything, I'm getting a 1/2, 0, negative I squared is 1 plus 1 is 2, negative 1 plus I squared is negative 1 minus 1 is negative 2, and then I minus I is 0. And of course, if I pass the 1/2 to all 4 terms, we end up with exactly what we expect to, 0, 1, negative 1, 0. The matrix we diagonalized. So that was a nice little verification just to make sure we did everything correct. Let's look at one more example. So our next example, we will do the matrix 1, negative 1, I, and negative I. So So this one we're starting with a bunch of i's in our matrix. And let's go ahead and diagonalize. And to diagonalize, we have to follow the process that we did before. We have to find all eigenvalues, eigenvector pairs, which in this case will take a determinant of 1 minus lambda I, negative I, and negative 1 minus lambda, which in this case will give me 1 minus lambda times negative 1 minus lambda. Then I'm subtracting negative I squared. And so what I'm left with when I FOIL is negative 1 minus negative 1 lambda, and then I have minus lambda, and then I have plus lambda squared, plus I squared is plus negative 1. And so I'm left with the lambdas canceling in the middle here, 2 copies of negative 1 and a lambda squared. I end up with lambda squared minus 2 is 0 for my characteristic equation. Or in other words, lambda squared equals 2. Or in other words, lambda is plus or minus root 2. Make it clear that I actually have 2 of these. I'll just write it as a positive root 2 and a negative root 2. So now that I've established those, let's just choose lambda as the positive root, and then compute 1 minus root 2, I, and negative 1 minus root 2 against x1, x2, and we want this to be equal to 0, 0. The top row is going to give me 1 minus root 2, x1 plus I, x2 is 0. The bottom row is going to give me negative I, x1 minus 1 plus root 2, x2 is 0. I can solve either one of these for one of the other. I guess it's maybe to my advantage. Let's go ahead and multiply the top one by I, and you'll see why in a bit. So I'm going to get I, 1 minus root 2, x1 minus x2, because of an I squared, that's where the minus sign comes from, equals 0. Or in other words, x2 is equal to I copies of 1 minus root 2, x1. I don't even need to solve anything for the second equation. It will always be extra information that I don't need. This is my relationship. And so I have something like x sub root 2, which is x1, x2, is going to be x1, and I can replace x2 with its notion here, I times 1 minus root 2 times x1, and then I can go ahead and just let those x1s be equal to 1, so that this x sub root 2 is really the vector 1, and I copies of 1 minus root 2. This is associated to lambda equals root 2. So my first eigenvector eigenvalue pair, and my second one will arise from lambda being negative root 2. In this case, I have 1 plus root 2 and negative I, and negative 1 plus root 2 against x1, x2 is equal to 0, 0. This gives me the system of equations. 1 plus root 2 x1 plus I x2 is 0, and negative I x1 plus negative 1 plus root 2 x2 is 0. I can play the same game I did before, multiply the entire first row by I to get I times 1 plus root 2 x1 minus x2 is 0, and this solves very quickly for x2 as being I times 1 plus root 2 x1. Now that's my relationship. My second line would have been extra information once again, so I don't really need it. This is my relationship. And we find out that x, the vector associated to negative root 2, is x1, x2, but I know x2 in terms of x1. In terms of x1, x2 is I times 1 plus root 2 x1, and I can let x1 be 1 to recover that my vector associated to negative 2 is 1, and I times 1 plus root 2 associated to lambda is negative root 2. So there's my 2 eigenvalues and eigenvectors. Then in step 2, we construct this capital X, which is just the 2 eigenvectors next to each other. And in this case, those are 1 and I times 1 minus root 2, as well as 1 and I times 1 plus root 2. Now x inverse is going to be a little bit more work to compute just because of that determinant term. I'm going to have 1 divided by AD minus BC It's going to be a little bit of work. So AD here is I1 plus root 2 minus I1 minus root 2. What I end up with is the positive I times 1 cancels with the negative I times 1, and I have really 2 copies of I root 2 in the denominator there. So this will simplify to 1 over 2 copies of root 2 times I. And 1 divided by I is the same as a negative I in the numerator. And then what else do I have to do when I invert a 2 by 2 matrix? I swap A and D around. So here's D, I times 1 plus root 2, and A goes in the bottom right. And I put a negative sign on B and C. And I can bring that down over here too. I times 1 plus root 2, negative 1, negative I, 1 minus root 2, and 1. And this is one of the cases where it's probably to my advantage to actually pull this into the inside, because there are so many i's sitting around, it wouldn't hurt for me to simplify them a little bit. So if I pull it in on the inside, I have negative I times I, those cancel, and I just have 1 plus root 2 divided by, let's keep a 1/2 out front and pull everything else in. So I'll take the 1 plus root 2 and divide by root 2, and the i's cancel. 1 divided by root 2 is 1 divided by root 2 plus 1, because that's root 2 over 2. And then distributed to the term on the right, I have negative signs canceling, and I end up with I divided by root 2. On the bottom, I end up with I times negative I gives me, or negative I times negative I gives me negative 1. And then I have 1 over root 2, so negative 1 over root 2. And then I have a minus 2 over root 2, but there was already a negative 1 there, so plus 1. Then I'll have a negative I over root 2 on the far right, and a 1/2 out front. So that's about as simplified as we're going to take x inverse, but I've established both of them. And then in step 3, we construct the diagonal matrix as, lambda 1, lambda 2 with some zeros. And in this case, lambda 1 is root 2, lambda 2 is negative root 2. Finally, in step 4, we combine everything. We find out our original matrix M, which was, I've already forgotten it, it was 1i, negative I, negative 1. 1i, negative I, negative 1. And this has to be equal to x d x inverse, which here, x is 1, 1, I, 1 minus root 2, I, 1 plus root 2, d, which is root 2, 0, 0, negative root 2, and x inverse, which was 1/2 times this matrix, which is a little ugly, 1 over root 2 plus 1, I over root 2, negative 1 over root 2 plus 1, and negative I over root 2. So there's the diagonalization of this particular matrix M. I won't go ahead and multiply these ones out. It would just be a lot of extra work, but it's kind of cool to see that even a matrix with i's in the beginning can actually have eigenvalues that aren't imaginary, and on top of that, have a really nice diagonalization still. I mean, the numbers aren't great, but it's not the end of the world either. Anyway, I'll stop there for today, keep it a little bit shorter. I hope it's all enjoyable. I'll see you in the next video. Bye.